Okay, so we've done comparison and limit comparison. Now let's go on ahead and do alternating series. Now, ladies and gentlemen, here's alternating series. If I have some sort of series that looks kind of like this. Boo, 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 boo. Okay, it's alternating because it goes positive, negative, positive, negative, positive, negative. Now, in this particular case, see the n plus 1 right here or the just regular n. Basically, it makes no difference. It's just that at n plus 1, it will start by being positive, but at n regular, it will start by being negative. So it doesn't matter whether it starts positive or starts negative. These just allow us to talk about both versions. Now, there's some conditions. Number one, if the next term is greater than 0 but less than the previous term, so the key here is they're getting smaller for each term. That's part of the key. So the difference between the terms has to keep getting smaller. And as long as the limit is not 0, well, why would the limit have to be not 0? Well, okay, that one would already be easy to determine. So that's why it's called alternating series. Now, let's go through an example. Here's a pretty clear example right here. Now, -1 raised to the n plus 1, but really all of it is just over n squared. So really we're saying, well, really it's just the same as this. So it's kind of like a comparison test in that what we're doing is we're just kind of ignoring the alternating component. And we say, well, let's take the limit as n approaches infinity. Well, obviously, we already know what's this series going to do. Converge. So if this is going to converge, all right, then we're probably going to have some convergence. So here's the question. Is the next term 1 over n plus 1 squared, is it greater than or less than 1 over n squared? Well, obviously we added 1, it's bigger, so this is going to be smaller. So is the difference getting smaller? Yes. Now, second, if I take the limit of this, if I take the limit of this function right here, just the part without the plus or minus 1, does this go to 0? Yes, this is a guaranteed converge. So does it get smaller each time? Yes. Does the limit itself go to 0 to converge? Yes. So therefore, the function itself must converge. Short version is alternating series test. As long as they get smaller, we're allowed to ignore the fact that they're alternating and just pretend that they're all on one side of the axis. Nothing more complicated than that. All right, next, this comes into the absolute and conditional convergence. Now, here's the deal. There's converges absolutely. Now, obviously, if I put the word absolutely in front of something, every time, 100%, versus if it's conditional, it means it only converges sometimes or under some conditions. So let's talk about this. If I have two series, a sub n and a sub n with an absolute value bar, okay, well, obviously, which one is going to test for absolute convergence? I'm going to go with the one with the absolute value bars, Bob. Okay, so good. Now, this comes into play because we know that 1 over n does what? Well, it actually diverges, doesn't it? Okay, but what about the alternating series 1 over n? Well, let's see here. That's going to be it's going to look very different. Since the alternating harmonic series converges, and they talk about using the alternating series test, so since the alternating harmonic series converges, the harmonic series diverges, well, what the heck? Well, it's conditionally convergent. All right, so if you just have a straight up harmonic, it's going to diverge. But if you have the alternating series harmonic, then it's going to converge. Well, let's think about this. This is the difference between sequence and series. In a series, you're add, and the harmonic's going to keep getting bigger, 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 bigger. But what happens if I have something that's alternating? I have 1, then negative 1/2, then positive 1/3, then negative 1/4. Okay, so in fact, this graph here is not really a great, that's a great sequence, but it's not a great series. Let's take a look at the series on this real quick. So we start at 1. Now what's 1 minus 1/2? Well, that's 1/2. What's 1 minus 1/2 plus 1/3? Well, that's going to go back up 1/3. But then we're going to come down 1/4. Okay, so then we're going to add 1/5. And before long, what do you see here? Well, because of the alternating nature, it's no longer harmonic because that doesn't alternate. But if we put the -1 thing in front, if it happens to be an alternating harmonic, then conditionally, so sometimes harmonic converges. But it's really only because of the plus minus plus minus. So that's what the absolute and conditional series, absolute and conditional convergence tests for. Excuse me. So if we have a series and it exhibits absolute convergence if the absolute value converges, all right, and if it exhibits conditional where the convergence, if one converges but the other absolute value diverges. So for example, this becomes conditional in our case because -1 raised to the n over n would definitely converge. But if I take absolute value of that, then it's going to diverge because it looks harmonic. Okay, as shown, they talk about this. So if an absolute value, however, does converge, then the whole thing converges absolutely. So if you have something that will converge, but when you take the absolute value, it diverges, that's conditional. If, for example, the absolute value 1 over n, let's go -1 raised to the n, n squared. Well, here's the deal. This is going to converge anyway, and the absolute value is also going to converge because it's over n squared, so that would converge absolutely. So it's convergent absolutely. All right, so it's really just a matter of semantics. So to give an example, let's take a look. In this particular case, you have, whoa, oopsie. You have this guy here. Ooh. All right, so we have, it's going to start with a positive number, but it's basically 1 over 3n plus 1 if I were to take the absolute value of it. Well, here's the problem. Does this converge or diverge? Well, let's see here. What's it really similar to? Well, it's really similar to 1 over n. Do we agree? Well, yeah, that's going to totally diverge. Is this greater than 1 over n every time? So we would say, yeah, that's definitely going to diverge either way. So we can see that the absolute value is this, and it diverges using limit comparison test. With harmonic, in fact, it's going to go to 1/3. Therefore, the series does not converge absolutely. However, if we put the negatives back in, boo, boo, and don't use absolute value, do we know that an alternating harmonic is actually going to converge? Yes. That means this is going to converge as well, so it converges conditionally. All right, converges conditionally. Versus, let's take cosine of 1 over n squared. Well, what would you compare cosine of n over n squared to? Well, here's the deal. You know cosine has to be between 1 and -1. So if I take the absolute value of this, I guarantee it's not bigger than 1. So the good comparison would be 1 over n squared. What does n squared do? Totally converges every time. So if this converges, then I can guarantee that converges. So, and it would converge absolutely because we use the absolute value bars. It converges, so therefore it converges absolutely. Now, we'll pick up ratio test in the next video.